All right, class, so this is an ALEKS topic that's called predicting the qualitative features of a line spectrum, and we are given this energy diagram that shows the energy levels of an electron. So these are really, we could think of these as orbitals, and we're sort of arbitrarily assigning them A, B, C, D, E. These are fictional. This isn't a specific molecule or atom or anything like that. But just sort of to help us understand what we're talking about when we talk about the different energy levels, which we now know are really orbitals, right? And then the electron transitions between those different energy levels or orbitals. So it says, use this diagram to complete the table below. And in the first question, it says, which is the ground state? So, it's a little bit unclear here how many electrons are in this system, I would say, which is a little confusing. But the ground state we're always going to sort of consider as the lowest state. So I'm going to say that A is the ground state. And I think when we're doing a problem like this, I think it just makes sense to think of sort of one electron and that one electron being able to sort of move around however we need it to move around. So for which is the ground state, I would choose A. And then the next question is, how many excited states are there? So every state above the ground state, we would consider that to be an excited state. So if I had an electron starting here, it could jump up to level B, it could jump up to level C, so on and so forth. So I count 1, 2, 3, 4 excited states. So all of these would be considered excited states, and we've got 4 of those. For how many lines are in the absorption? So here we really have to be careful about what we're talking about, absorption or emission, just to sort of keep everything straight in our minds. So how many lines are in the absorption line spectrum? So anytime, let's imagine we had an electron here, and that electron jumped up to this higher energy level B. The reason that it would do that would be because it absorbed some energy. So a photon comes in, hits that electron, the electron absorbs energy, and it jumps up to a higher energy to an excited state, which would be B. So every time it does that, it will absorb that photon of that energy. So this says how many lines are in the absorption line spectrum. So the way to count this, because it's really not just from A, the ground state, up to these other energy levels, this question is really going to be asking all of the possible, transitions. So an electron could jump up to B, but then that electron from B could jump up to C or could jump up to D. So we're going to have a lot of different sort of options here. So the way that I would count this from A, just starting from A, we could go from A to B, A to C, A to D, and A to E. That's 1, 2, 3, 4 transitions so far. So we'd start with 4. So I might just write that over here, 4 plus, just to sort of keep track. Then from level B, we could go up to C, up to D, and up to E. So that would be 1, 2, 3 more. And we can do the same thing for if that electron now starting in level C, it could go up to D or E, so that's 2 more. And then the last one would just be from D to E. So this equals 10 in total. So for this system, I count 10 different possible absorptions of energy that could occur. And it is a little confusing to say that the electron is then already in the excited state D and it's still going to absorb more energy and jump up to E. So realistically, it's not very likely, but it is certainly possible. And as long as it's possible, then we need to sort of take that into account. And so here I would count 10 lines in my absorption line spectrum, 10 possible transitions. All right, the next question is, which transition causes emission at the shortest wavelengths? We need to sort of go through that logical progression. What does shortest wavelength mean? How do we correlate that to the energy of the photon? So if it has a very short wavelength, then that means it has a higher energy. So I'll just sort of make some notes here. Shorter wavelength equals greater energy. So the way that I sort of think about that, personally, I just think about that, the fact that higher energy photons are having a greater frequency and a shorter wavelength. If you need to go through the different equations, you can sort of say, well, I know that C equals wavelength times frequency, and energy equals Planck's constant times frequency. So if I'm looking for the shortest wavelength, that's going to be the highest frequency. So as this goes down, this should go up. If this goes up, that means the energy also has to go up, since h is going to be Planck's constant. It's going to be constant. So basically, getting back to our question, which transition causes the emission line? So emission is going to be where we're going down in energy and emitting a photon at the shortest wavelength. So this is going to be our biggest transition. So this is really going to be E to A. So as an electron goes from the E excited state all the way, relaxes all the way down to the ground state, that's going to be the biggest energy transition, and it's going to give off the wavelength of, or the photon of light with the shortest wavelength. For the bottom one, which transition causes the emission? Again, we're talking about emission. We have to be careful about that. At the longest wavelength, so just like we said before, shortest wavelength is going to be the greatest energy. Longest wavelength is going to be the smallest amount of energy. So here I'm looking for the smallest transition. Which one is my smallest transition? And I can see that from C to B, that's going to be my smallest transition. So again, if we want to do an emission, we're going to go from the higher energy to the lower energy, C to B. As it relaxes back down from C to B, it's going to give off a photon of light. Okay, hopefully this clears up any questions you have about this ALEKS topic, predicting the qualitative features of a line spectrum. If you have any other questions about these, feel free to let me know.